we're at the start of what is potentially a tricky week, so I've got a few videos that I'm going to do just to make sure that we understand what's going on here. The first thing we're going to look at is infrared spectroscopy, which is another analytical technique that we use in organic chemistry, and it comes down to the fact that all bonds in molecules absorb infrared radiation, and in terms of the way that they absorb the infrared radiation, they can either absorb them in what they call a stretching vibration, which is when the atoms in the bond kind of vibrate back and forth, that's this one here, or they can absorb infrared radiation by what they call a bending vibration, which is what we've got going on in this one here. The only way I can really liken all of this, if you think about when you're on a bus and then the bus comes to a standstill, and then all the bars and the kind of windows start to vibrate, and the reason that they vibrate is because the natural resonating frequency of the windows and the bars just happen to match the frequency of the engine at the back of the bus. This is exactly the same. The natural resonating frequency in the covalent bond just happens to match some specific and unique frequency in the infrared region of the electromagnetic spectra. Now, the reason that the have their own unique specific frequency is because of several factors, basically, and the three are outlined here. So the strength of the bond determines what frequency it's going to naturally resonate at. The bond length is also going to determine what frequency it's going to naturally resonate at, and then the mass of the atom at either end of the bond. And if you kind of think about the electromagnetic spectrum, remember the electromagnetic spectrum is absolutely huge, and then the visible region is some narrow band somewhere in the middle there, and if you've got the kind of X-rays at this end, that's the high energy stuff. The lower energy stuff, and remember you've got red through to violet in the visible spectrum. So infrared just sits about there, and even if we were to look at the infrared region, it is a range. Okay, so very small range when you look at the entire frequency range that you get in the electromagnetic spectrum, but if we kind of have a look at just that, we get a range. So here's how infrared spectroscopy works. So it basically works on the basis that we have an infrared light source where we can literally start to turn the frequency up. We then have a sample with our molecule in at this point here, and what we get at the other end is a detector which detects infrared radiation. So of course, if the bond is absorbing infrared radiation, less of it will reach the detector. Okay, and then what you get is a chart which we call a spectra, which shows you which frequencies of infrared radiation in this range here have been absorbed and which ones haven't, and it's that gives us clues to bonds that are present in the electromagnetic spectrum. So essentially what happens then is in the machine here, we start from a low infrared frequency, and it's gradually turned up all the way to a high infrared frequency. And let's say, for example, that at one point here, as we're turning it up, a specific bond will start to vibrate and absorb some of that infrared radiation. As we continue to turn it up, the infrared will pass through, and then again there might be another bond in that molecule that will absorb a specific frequency of infrared radiation. Now in chemistry we don't use frequency. What we talk about here is wave numbers, which essentially is frequency, because wave numbers is essentially the number of waves that pass per second, and of course that, if you think about it, is really frequency. Okay, so here's a typical kind of infrared spectra that we get here. Now, you're going to need your data sheet, and if you haven't got your data sheet, you're going to need this section here while you're doing any questions about infrared spectroscopy. Now, what we've got here is we've got the bonds, and then we've got the frequency, which of course we call wave numbers, in this region here, okay? And what we've got is the frequencies at which specific bonds start to vibrate. So, for example, between 750 and 1100, we get carbon-carbon bonds vibrate and absorb infrared radiation. And of course, that's not particularly useful in organic chemistry, because organic chemistry has a lot of carbon-carbon bonds. So let's just have a look at the spectra now, and we'll have a look at kind of what this scale means at the side here. So if you look at the scale on the side here, we start at 0. We talk about transmittance, so it's how much has gone through. So when none has gone through, it means it has absorbed infrared radiation. And then at the other end up here, we've got 100% transmittance. So that means nearly all of it has gone through. So what we get is this kind of red squiggle that we've got all the way along here. So we call things like this, I'll just put a star in it in blue, we call this a peak, even though it actually looks more like a trough. But it's a peak because this is the absorption of infrared radiation that is being absorbed by a specific bond. And if you kind of look at where it is, so we've got this bit here, and we've got it between 2,500 and 3,300, which means it's possibly going to be that one, okay? And then we've got another peak here. And again, if we look where that one is there, so that one looks like it's going to be this peak vibrating here. So here's the key thing then. So we start off and we basically change our infrared radiation as we go through our molecule. You'll see the certain specific frequencies. There's one there, there's a second one here, there's third, fourth, and so on and so on and so on, where infrared radiation is being absorbed due to specific bonds in that molecule vibrating. Okay, now this is really useful because what it allows us to do is identify what functional groups are present in a molecule and which ones are not. Now, there is a region in here that is less useful than other key peaks, and that one is this region here that is outlined in green. We call it the fingerprint region. Now, the peaks in here, although you can't really determine anything particularly with what's going on here, we call it the fingerprint region because this section of peaks here is unique to each and every molecule. So even though we use the infrared spectra to identify key bonds, for example, that one there and this one here, what tends to happen these days is when you put a sample through an infrared spectra machine, yes, it identifies the key peaks, but what it then does is it takes a kind of a shot of that and compares it against a spectral database, which then allows you to identify exactly what that molecule is. Okay, so that's really what infrared radiation is. Infrared spectroscopy is all about. Okay, so the best way really to think about these is to have a look at them, and the key thing about infrared spectroscopy is the peaks that are not there are as important as the peaks that are there, because if we look at this one here, we haven't got any significant peaks in this region here. all right? I know we've got these little peaks here and here, but we're talking at peaks that get down to about this level here, okay? So we've got no peaks there. So if we have a look at what we haven't got between 2000 and 4000 back up on here, what that means is that in that molecule, we don't have any of those, okay? So, you know, that's the kind of thing that we're talking about when we're looking at these. Now, there's certain key peaks that you need to kind of look out for or be aware of. And of course, you can't do any of these without the data sheet. And as I say, if you haven't got the data sheet, you need to use the previous page in here. So this peak here, the one I'm about to kind of put a star on, that peak there, if you look at where it is, if you read where it is on this scale here, it's about there, which is at 1700, okay? And here's how you would word it in an exam question. You'd say, there is a peak at 1700, which falls in between 1680 and 1750, which means we have a carbon-oxygen double bond, which of course, if you remember, we call a carbonyl. So this key peak here is a carbonyl peak, which is basically telling you it is very likely to be an aldehyde or a ketone. It can't be a carboxylic acid because we don't have any OH peaks the way you'd normally find them there. Okay, so just having a look at the next one. So, and again, just look at the key peak. We've got a key peak at this point here. All right, and again, if you look at where that one is, so if I go down to here, so that's 1, 2, 3, that's about 3,350. So if you have a look at where that one is, so 3,350, 3,350 is going to be this one here, because it falls in that range there. And it's an OH peak that's in alcohols. And again, when you talk this through in an exam, you'd say, I have a peak at 3,350, which falls between 3,230 and 3,550, which means it is an OH in alcohols. And that is very different to where you find the OH in carboxylic acids, okay? The other thing about OH peaks or alcohol peaks is that they do tend to be broad, all right? When we say broad, we're talking about them being wide, so you can see that that's quite wide there. Okay, so that's the key thing with that one. So let's move on to the next one. So this would be a good point to have a go at these questions here. So it's literally looking at key absorptions that you'd see in these molecules as we go through, and that is one of your homework. So it'd be worth having a go at the quiz first in the document that I've sent you, and then have a go at these questions through here, okay? And again, the way to remember, you know, with all spectroscopic techniques, they just give you an extra clue. It's a bit like a detective story. You get a little bit of clue from infrared spectroscopy. You get another clue from working out the empirical formula and the molecular formula. You know, you put all these clues together. You get the MR from the mass spec. And of course, all of these things together give you little bits of clues, which then together give you quite a powerful analysis tool. Okay. I will just talk about this as well, because it's these bonds in the molecules that are naturally in the atmosphere that basically cause global warming. So radiation from the sun hits the planet, and it's absorbed by the planet, and then the energy is re-emitted back out into space as infrared radiation. And although most of it does go back out into space, some of it gets trapped in the atmosphere, because basically what happens if you kind of look at, if we look at these molecules here, we have quite a lot of water in our atmosphere, and we also have quite a lot of carbon dioxide in our atmosphere. Okay, and you can see these molecules can do all sorts of vibrations, stretching and bending vibrations. We don't need to worry about the types of vibrations that occur, but you do need to know that these are the molecules that absorb infrared radiation. Okay, and that basically traps that energy in the atmosphere, which is why we have kind of global warming. Some of the molecules naturally should be there. For example, water is naturally in the atmosphere, and that's why the planet is slightly warmer than it would be if it didn't have an atmosphere. Of course, carbon dioxide, there should be a certain amount of carbon dioxide, but with the excessive use of fossil fuels, that is on the increase. And of course, because that is now in the atmosphere, more concentrated in the atmosphere, more infrared radiation gets kind of trapped in the atmosphere, global warming. So there's basically three things that contribute to how effective something is as a greenhouse gas, and therefore could be a contributor towards global warming. How much of it is in the atmosphere, its ability to absorb infrared radiation, and an example of that is methane is very, very good at absorbing infrared radiation, a lot better than carbon dioxide. There just isn't as much of it in the atmosphere. And the third one is how long is it there in the atmosphere? Okay, and all of these things together give you the global warming potential. Okay, so that's a good point to start. So we'll stop there and we'll look at the next technique in the next video.